Imagine for a moment you're just browsing your favorite website or quickly checking your bank balance. A seemingly simple action, right? But what happens behind the scenes if a tiny, obscure component in that vast digital infrastructure fails? Leslie Lamport, a brilliant mind in computing, put it perfectly. A distributed system is one in which the failure of a computer you didn't even know existed can render your own computer unusable.
It's a profound thought. Yeah, it really encapsulates the hidden complexity of our digital world. The magic and sometimes the mayhem happens when these thousands, maybe millions of independent computers, often owned by different organizations, have to somehow work together to deliver that one simple thing you're trying to do.
That's fascinating. We think of the internet as this seamless thing, but it's actually a vast collection of independent, potentially unreliable pieces. Today, we are taking a deep dive into that fascinating world, the realm of large-scale distributed systems. Our guide for this journey is Roberto Vitillo's Understanding Distributed Systems, second edition.
Right. And our mission really is to unpack the core concepts, the common challenges, and honestly, some truly elegant solutions. These are the things that allow applications like Google, Netflix, Dropbox, you name it, to handle millions of users, store just vast amounts of data, and remarkably, stay resilient even when things inevitably go wrong. We're aiming to cut through the jargon, give you the essential insights and maybe those genuine aha moments you need to feel truly well-informed about how the digital world really works.
Because whether you're prepping for a technical meeting, trying to grasp the architecture of modern apps, or maybe you're just intensely curious about the magic behind your favorite online services, well, understanding distributed systems is key. You'll discover why building them is so essential. I mean, from managing inherently distributed applications like the web itself to ensuring high availability.
Like Dropbox replicating your data across multiple servers, exactly.
Yeah, or handling massive workloads.
Think Google's search requests, like tens of thousands every second, or meeting strict performance requirements like Netflix streaming high-res movies seamlessly because they've got data centers geographically close to you.
Right. And Vitillo's book organizes these complex challenges into 5 core pillars: communication, coordination, scalability, resiliency, and maintainability. So we're going to explore each of them, starting with the very first challenge. How do these independent systems even talk to each other? Let's dive into communication.
Indeed. The fundamental hurdle, the first thing you hit, is reliable communication over networks that are inherently fundamentally unreliable. It's a classic example of the law of leaky abstractions. Think of it like driving a car. The abstraction is just drive, right? But if you ignore the underlying leaks like low tire pressure or engine oil, you'll eventually break down. Similarly, network libraries give you this easy interface, but some fundamental problems like packets just getting lost that can't be completely hidden away.
Okay, so we need to understand what's happening underneath that abstraction. At the lowest level, you've got the Internet Protocol, IP. This sends basic packets, but here's the catch, right? IP doesn't guarantee delivery. Packets can be dropped, duplicated, maybe even corrupted.
Exactly. So to build reliability on top of that chaos, we use the Transmission Control Protocol, TCP. It's truly a marvel of engineering when you think about it. TCP takes a stream of bytes, chops it into segments, numbers them, and then uses acknowledgments. If a segment isn't acknowledged by the receiver within a certain time, a timer fires back at the sender and bam, it's retransmitted. Plus, it uses checksums to ensure data integrity. The real genius of TCP isn't just delivering the data, it's creating the illusion of a perfectly reliable connection, like a wire on top of the messy, unpredictable internet.
But even with all that cleverness, the physical limits, distance, network congestion, those are often the real bottlenecks you hit first, aren't they? Even TCP has its quirks, like the cold start penalty from its three-way handshake. That's a full round trip before any actual application data gets sent.
Right. And that's precisely why putting servers geographically closer to clients is so crucial for faster connections. Reduce that round trip time.
Makes sense.
And TCP also does something called congestion control. The sender keeps track of a congesting window, which basically limits how many segments can be in flight without an acknowledgement. This mechanism prevents the sender from just flooding the network in overwhelming routers. The key takeaway: your network speed isn't just about raw bandwidth, those megabits per second. It's fundamentally limited by latency, how quickly a signal can travel back and forth. So latency is often the real performance killer, especially for interactive stuff.
Okay, so TCP gives us this incredibly robust, reliable channel. But sometimes, maybe that very robustness, that reliability comes with a cost. Like, it's actually a hindrance for some apps.
That's a great point. And that's where UDP, the User Datagram Protocol, comes in. It's a faster, connectionless alternative. No handshake, no guaranteed delivery, no ordering. A really compelling example where UDP shines is in multiplayer games. Think about it. Clients are sending gamepad events constantly. Servers are blasting out game state snapshots multiple times a second. If one of those state snapshots gets lost, there's zero value in TCP, meticulously retransmitting that old, obsolete data. The game world has moved on. TCP would try to redeliver, potentially causing lag and degrading the experience, whereas UDP just sends the next snapshot. It's ideal for real-time, less critical updates where speed matters more than perfect reliability.
Okay, that distinction is clear. Now, once you have that communication channel, whether it's TCP or UDP, you need to secure it, right? Especially on a public internet.
Absolutely. That's where Transport Layer Security, or TLS, comes in.
Yeah.
It runs on top of TCP, usually, and encrypts the communication. It provides confidentiality through encryption, authentication so you know who you're talking to, and integrity so the data hasn't been tampered with.
And how does it establish that trust, the authentication part?
TLS uses digital certificates to prove ownership of a public key. These certificates are issued by trusted third parties called certificate authorities, or CAs like Let's Encrypt, which is a really popular free one. These CAs form a chain of trust that verifies the server's identity before you send any sensitive data. But similar to TCP's handshake, this TLS handshake also introduces some initial overhead, another round trip. So again, server proximity and reusing existing connections help minimize that latency penalty.
Got it. Okay, next up in the communication stack, the Internet's phone book, DNS, the domain name system. This is, as you said, like a globally distributed, hierarchical, and importantly, eventually consistent key value store. When you type a URL, your browser needs to turn that friendly name into an IP address.
Exactly. And the resolution process is quite layered. First, your browser checks its local cache. Maybe you visited the site recently. If it's not there, it asks your operating system's DNS resolver. If that doesn't know, the resolver starts querying up the hierarchy. It might ask a root name server, which points it to the correct top-level domain or TLD server, like virtualiotom or .org. That TLD server then points to the authoritative name server for the specific domain you want, like google.com. And finally, that authoritative server provides the actual IP address.
And crucial to how all this works efficiently is the time to live, or TTL, right, on those DNS records.
Yes, TTL is critical. It tells caches your browser's cache, the resolver's cache, how long they can hold on to that IP address before they need to ask again. Set the TTL too long, and if the IP address changes, users won't see the update quickly. Set it too short, and you hammer the authoritative name servers with constant requests, increasing their load. It's a trade-off. And the surprising, maybe slightly scary takeaway here is that this seemingly simple system, DNS, can easily become a single point of failure. If a key name server goes down, it can lead to absolutely massive outages for services that rely on it.
Wow. So that dependency is pretty fragile.
It can be. And this vulnerability really highlights the importance of designing for what's called static stability. Ideally, systems should try to continue functioning, maybe in a degraded way, even when their dependencies are impaired. Imagine your browser's DNS cache managing to serve a slightly stale but still working IP address during a DNS outage, rather than just giving up entirely. It's about graceful degradation instead of total collapse.
Okay, so we have the IP address via DNS. We have a secure channel, maybe via TLS over TCP. Now we can actually talk to the services using APIs. HTTP APIs, often built using RESTful principles, are really central here. They tend to use stateless requests and encourage cacheable responses.
Right, and the evolution of HTTP itself is interesting. We had HTTP 1.1, which suffered from head-of-line blocking, basically. You couldn't send a new request on a connection until the previous response came back fully. Slows things down. Then came HTTP 2, which improved things with multiplexing over a single TCP connection. And now we have HTTP 3, which is built on top of UDP, believe it or not, using a protocol called QUIC. This fundamentally solves head-of-line blocking because packet loss in one stream doesn't block other independent streams on the same connection.
And within these APIs, URLs model the resources, like Products 42 reviews. JSON is super common for the data representation. And then you have the HTTP methods, get, post, put, delete, defining the actions.
Exactly. And understanding the nuances of these methods is crucial in distributed systems. Get is defined as safe, meaning it shouldn't have side effects, like changing data, and because it's safe, responses can often be cached. Put and delete are typically defined as idempotent. This is a key concept. It means executing the same request multiple times has the exact same effect as executing it just once. Like setting a value with PUT multiple times still results in that value being set. Deleting something multiple times still results in it being deleted.
But PST is different, right? It's neither safe nor idempotent, generally.
Correct. PST is typically used for actions like creating a new resource or triggering a process that might have side effects each time it's run.
And this distinction, especially idempotency, becomes incredibly important when dealing with network uncertainty. Think about retrying requests. If a client sends a POST request to create a new product, the request goes through, the product gets created on the server, but then the network connection drops before the success response gets back to the client. The client sees a timeout. What does it do? It retries the POST.
Right. And if that POC isn't handled idempotently by the server, boom, you suddenly have two identical products created. That's usually a big problem.
So how do APIs handle that?
Well, this is where the principle of least astonishment comes into play. Good API design tries to handle these scenarios gracefully. Maybe the server can detect it's a duplicate request based on some unique ID the client sent and just return the original success response. For really critical operations where you absolutely cannot tolerate duplicates or partial effects, you might rely on ACID transactions, especially if the request identifier and the resource being modified live in the same underlying database. Remember ACID? Atomicity, all or nothing, consistency, valid data states, isolation, concurrent operations don't interfere, and durability. Once committed, it's permanent. But achieving full ACID guarantees in a distributed world across multiple independent services, well, that becomes a monumental challenge.
Okay, that perfectly sets up our next big topic. We've talked about communication. Now let's shift focus to the core problem of coordination. Getting all these different nodes or services to work together in unison, especially when failures are happening all the time.
Exactly. And the inherent difficulty of this is beautifully illustrated by the famous two generals problems, classic thought experiment. Imagine two allied generals, their armies camped on opposite hills overlooking an enemy city in the valley below. They need to agree on a specific time to launch a coordinated attack. They can only communicate by sending messengers across the valley, but any messenger might be captured by the enemy. So General A sends a message, attack at dawn. How does General A know General B received it? General B sends back an acknowledgement, got it, attacking at dawn. But now, how does General B know General A received the acknowledgement? General A needs to acknowledge the acknowledgement, and you see the problem.
It's an infinite loop. Neither can ever be 100% certain the other got the final confirmation needed to proceed.
Precisely. No matter how many confirmations you send back and forth, you can never achieve absolute certainty of agreement over an unreliable communication channel. It's a classic. For a reason, you can almost feel the general's frustration. It really hammers home just how fundamentally difficult agreement is when communication isn't guaranteed.
Which naturally leads to the tricky concept of time in distributed systems. Our normal clocks aren't quite reliable enough, are they?
Not really, no. Physical clocks, the ones based on quartz crystals in most computers, suffer from clock drift. They tick at slightly different rates. Over time, this leads to clock skew, where the times on different machines diverge. We use protocols like Network Time Protocol, NTP, to try and synchronize them with authoritative time sources. But NTP synchronization isn't perfect. It can cause clocks to jump forwards or backwards suddenly, which makes physical time unreliable for accurately ordering events that happen very close together across different nodes.
So if physical time is shaky, how do we reason about the order of events?
We turn to logical clocks. The most famous are probably Lamport clocks, named after Leslie Lamport again. Lamport clocks don't measure physical time in seconds or milliseconds. Instead, they assign ever-increasing countervalues to events within a process and include these timestamps in messages. The key idea is to capture the happen-before relationship. If Operation O1 causally happened before Operation O2, maybe O1 sent a message that O2 received, then Lamport's algorithm ensures O1's logical timestamp will be less than O2's. It gives you a partial ordering based on causality.
And there are other types too, like vector clocks.
Yes. The vector clocks take this a step further. They maintain a vector of logical clocks, one for each process in the system. They provide a stronger guarantee. If one vector timestamp is strictly less than another, then a causal relationship must exist between the corresponding events. They can detect concurrent events that Lamport clocks might not distinguish. So while physical clocks are fine for, say, correlating log entries for debugging, they generally aren't reliable enough for critical ordering logic across different processes. Logical clocks are the tool for that.
Okay, so ordering is tricky. Sometimes, though, you don't just need ordering. You need one specific process to be in charge, to have special powers, like being the only one allowed to write to a shared resource. This is leader election.
Right, and the Raft consensus algorithm is a very widely used and, relatively speaking, understandable solution for electing a leader and keeping it elected reliably. There are practical considerations, of course. For instance, when nodes suspect the leader has failed, they start an election. To avoid a split vote, where multiple nodes get roughly the same number of votes and no one wins, each node waits a randomized election timeout before starting an election. This staggering usually ensures one node emerges quickly.
Do people typically write these algorithms like Raft from scratch?
Rarely, actually. Implementing consensus algorithms correctly is notoriously difficult. More often, systems rely on existing battle-tested libraries or foundational services. For instance, many systems use fault-tolerant distributed key-value stores, like etc. or Zookeeper, which provide primitives like atomic compare and swap operations. You can use these primitives to build reliable leader election on top. But having a single leader isn't a silver bullet. It can become a scalability bottleneck because all writes might have to go through it, and it's also potentially a single point of failure if it crashes and the election process takes time.
Which brings us nicely to replicating data, making copies to handle failures, and maybe improve read performance.
Exactly. The foundation of building fault-tolerant services is often state machine replication. The core idea is simple. You have a service, the state machine, and you run multiple identical copies, replicas of it. You have a leader that receives client requests, operations. The leader sequences these operations and broadcasts them to the followers, the other replicas. If all replicas execute the same deterministic operations in the same order, their states will remain consistent. If one replica fails, the others can continue operating. You have redundant copies.
And Raft plays a role here too, right?
Yeah.
Beyond just leader election.
Yes. Raft includes a replication protocol as well. The leader appends incoming client operations to its own log. Then it sends appended trees requests containing these new log entries to its followers. An entry is considered committed, meaning it's safe to apply to the state machine and return a result to the client only when a majority, a quorum, of servers, including the leader, have durably stored that entry in their logs. This majority requirement is key. It allows the system to tolerate the failure of a minority of servers while still making progress. And crucially, those appended trees requests are designed to be idempotent. If a follower receives the same request multiple times due to network issues, applying it again doesn't mess up its state.
Okay, now we're getting into an area that really shifts how people think about data in distributed systems. Consistency models. This can get pretty subtle. Let's start with the strongest. Linearizability.
Right. Linearizability, sometimes called strong consistency or atomic consistency, provides the strongest guarantee, typically for operations on a single object or key. It means that all operations appear to take effect instantaneously at some single point in time, and they appear in a single global real-time order. It's like there's one single copy of the data, and every read sees the absolute latest committed write. It behaves as if the operations were executed sequentially on a single machine. It's the most intuitive model, probably.
But intuitive often means expensive, right? What's the cost?
The cost is often latency, especially for reads. To guarantee linearizability, a read operation often requires the leader node to contact a majority of replicas to confirm that it is still the leader and hasn't been deposed by a network partition it wasn't aware of. This confirmation step adds network round trips and increases read latency.
Okay, so what are the alternatives if linearizability is too slow?
Well, there's a spectrum. Sequential consistency is slightly weaker. It still guarantees that all processes see operations in the same single global sequence, but that sequence might not match the real-time order. A process might observe operations slightly out of sync with wall clock time, but everyone agrees on the order. Think of a synchronized queue. Consumers see items in the order they were produced but might lag behind. Then you have much weaker models, like eventual consistency. This simply guarantees that if no new updates are made to an object, eventually all replicas will converge to the same value. It doesn't say when or in what order intermediate states might be observed.
This is where the famous CIP theorem comes in, isn't it? Consistency, availability, partition tolerance, pick two.
Yes, CAP. It's widely known, but also widely misunderstood. The theorem states that in the presence of a network partition, where nodes can't communicate a distributed system, must choose between consistency, C, and availability, A. Consistency here usually refers to linearizability. Availability means every non-failing node can process requests. The crucial point often missed is that perfect availability, as defined by CAP, every request gets a response, is practically impossible in real-world systems anyway due to timeouts and other failures. And consistency isn't binary. It exists on a spectrum. So rather than a strict pick two, it's more about understanding the trade-offs you make, especially during partitions. A related concept, the Pace-LC theorem, tries to offer a more nuanced view. It suggests that even without partition else, there's often a trade-off between latency L and consistency C, or latency and availability A.
Interesting. Are there other replication strategies besides raft-style leader-based ones?
Yes, chain replication is a fascinating alternative that also provides strong consistency. Linearizability. In a chain, you have nodes ordered linearly. Writes only go to the head of the chain. Each node processes the write and forwards it to the next node in the chain. Only the tail node acknowledges the write back to the client. This means write latency is high because it has to traverse the entire chain.
That sounds slow for writes. Why would you use it?
Because reads are interesting. Reads would be served by any node in the chain, but typically they are directed only to the tail node. Since the tail only sees writes after they've been processed by all previous nodes, reads from the tail are guaranteed to be linearizable. And while individual write latency is high, the throughput can be very high because you can pipeline writes, the head can start processing the next write while the first write is still propagating down the chain. It also neatly separates the data plane, handling client requests, which doesn't need a leader once the chain is set up, from the control plane, managing chain configuration, which does need consensus for fault tolerance.
Okay, so we've got consensus-based replication. What about avoiding consensus altogether to get better performance or availability?
Right. That's coordination avoidance. The idea is to replicate data without needing strict agreement or a single leader for every write. This is where things like conflict-free replicated data types, or CRDTs, come in. These are data structures designed such that concurrent updates made on different replicas can always be merged automatically without conflicts, leading to eventual consistency. Think of counters you can only increment, or sets you can only add to.
And systems like Amazon's Dynamo or databases inspired by it like Cassandra?
It's exactly. Dynamo-style data stores are a prime example of coordination avoidance for writes. Typically, any replica can accept reads and writes for the data it holds. To provide some level of consistency and durability tuning, they use quorums. You configure a write quorum, WD the number of replicas that must acknowledge a write for it to be considered successful, and a read quorum are the number of replicas that must respond to a read request. The key insight, or rule of thumb, is that if you configure W plus Rn, where n is the total number of replicas for that data item, then any read quorum R is guaranteed to overlap with the most recent write quorum, WW, by at least one node. This ensures that a read will always see at least the effects of the most recent successful write, providing a form of eventual consistency, though not linearizability on its own. It trades strong consistency for higher availability, especially during network partitions.
Let's wrap up coordination by talking about transactions again, but specifically in the distributed context. We mentioned ACID properties earlier.
Right. ACID, atomicity, consistency, isolation, durability, is relatively well understood within a single relational database. But implementing transactions that span multiple independent data stores, maybe across different microservices, is significantly harder. How do you guarantee atomicity, all parts succeed or all fail, when the databases don't even know about each other?
That sounds like a major headache. How do systems even attempt that?
One traditional and somewhat notorious approach is the two-phase commit protocol, or 2PC. It involves a central coordinator process and several participant processes, the different databases or services involved. In Phase 1, the prepare phase, the coordinator asks all participants if they are ready to commit the transaction. Each participant tries to do the work locally, locks the resources, and responds yes or no. If all participants say yes, the coordinator moves to Phase 2, the commit phase, and tells everyone to commit permanently. If any participant says no or times out, the coordinator tells everyone to abort and roll back.
Okay, sounds logical. What's the catch?
The big catch is that 2PC is blocking. While waiting for the coordinator's final decision in Phase 2, participants have to keep resources locked, potentially for a long time if the coordinator is slow or crashes, and the coordinator itself is a single point of failure. If it crashes after sending the prepare message, but before sending the final commit or abort decision, the participants are left in limbo, unsure whether to commit or roll back. They might be stuck holding locks indefinitely. Despite these drawbacks, sophisticated versions of 2PC are used in some large-scale systems like Google Spanner, which combines it with globally synchronized clocks, true time, to make it work across partitions, but it's inherently complex.
So blocking is bad. What are the modern, more flexible non-blocking approaches?
To get around the blocking nature, we often turn to asynchronous transactions, sometimes drawing an analogy to a cashier's check. You deduct the funds from your account, local transaction, then the check is physically transported, message passing, and deposited later, another local transaction. It's non-blocking, your account is debited immediately, but there can be intermediate inconsistencies. The recipient doesn't have the money yet. A very practical implementation pattern for this is the outbox pattern. When a service performs an action that needs to trigger something else, like sending a notification or updating another service, it does two things within a single local database transaction. One, it makes the change to its own data, and two, it appends a message describing the event to a dedicated outbox table in the same database. Because this is a single local transaction, it's atomic. Then a separate relay process monitors this outbox table, picks up the persistent messages, and reliably sends them to a message channel, like Kafka or RabbitMQ. The relay uses idempotency keys or checks to handle potential duplicate message deliveries if the relay itself fails and restarts.
Okay, that handles triggering events reliably. What about complex business processes that involve multiple steps across different services, like booking travel?
For those complex, potentially long-running distributed workflows, the saga pattern is often used. Think of booking a trip. You need to book a flight, then a hotel, then maybe a rental car. Each is a separate service, a separate transaction. A saga orchestrates this sequence of local transactions. Crucially, for each step in the saga, for e.g. book flight, there must also be a defined compensating local transaction, e.g. cancel flight booking. If any step in the saga fails, the orchestrator executes the necessary compensating transactions for all the preceding completed steps in reverse order to effectively undo the overall business operation. This achieves atomicity, the whole trip is booked or nothing is permanently booked, but without requiring global locks or 2PC.
So it guarantees atomicity eventually, but allows for temporary inconsistencies.
Exactly. Sagas rely on orchestrators, or sometimes choreography between services, to persist the state of the long-running transaction, and the participating services must be designed to handle potentially duplicate requests or messages. It's fundamentally about making a best guess that the subsequent steps will succeed, and having a reliable mechanism to apologize and clean up using compensating actions if something goes wrong along the way. It gives you atomicity, but in a non-blocking, eventually consistent manner, which is often a much better fit for loosely coupled microservice architectures.
So we've covered how systems talk, communication, and how they try to agree or coordinate actions, coordination, even across unreliable networks. But what happens when you need those conversations and agreements to handle not just dozens, but millions or even billions of interactions? That brings us to the monumental challenge of building for scale, making it truly big. Imagine scaling a simple web application, what Vitillo calls a CRUDER app. Create, read, update, delete from running on a single machine to handling millions of requests per second.
Right. The first instinct might be scaling up, just buying a bigger, faster, more expensive server with more CPU, RAM, and storage. And that works for a while. But eventually you hit a physical and economic brick wall. There's a limit to how powerful a single machine can be. The long-term solution, and really the core philosophy behind most modern large-scale systems, is scaling out, adding more machines, usually commodity hardware, and distributing the load across them. This introduces complexity, definitely, but it's the only practical way to handle truly massive workloads efficiently and cost-effectively.
And this scaling out often starts with decomposition and specialization, right? Breaking things apart.
Precisely. A very common first step is functional decomposition. For instance, taking the database that was running on the same machine as the web server and moving it to its own dedicated database server. That's a simple form of specialization. Another key strategy, especially for web apps, is offloading large static files, images, videos, CSS, JavaScript to dedicated managed file storage services. Think AWS S3, Azure Blob Storage, Google Cloud Storage.
Why is that so effective?
Because these services are purpose-built for exactly that. Storing and serving vast amounts of data with extreme scalability, very high availability, and strong durability guarantees, like automatically replicating your data across multiple physical locations. They also often integrate seamlessly with content delivery networks, CDNs, allowing users to fetch those large files directly from a server geographically close to them, which massively reduces the load on your core application servers.
Okay, offloading static files helps. What about caching dynamic content or results?
Yes. Smart caching is absolutely vital for scale. We touched on client-side HTTP caching earlier, using headers like cache control and etag. This tells browsers or intermediate proxies that they can reuse a previous response for a certain period, avoiding requests to your origin server altogether. This idea of separating reads, queries from writes, commands for optimization is also reflected in architectural patterns like command query responsibility segregation or CQRS, although that's a broader concept.
And then there are CDNs, content delivery networks. How do they fit in beyond just static files?
CDNs take caching to a global scale. They are essentially overlay networks of thousands of caching servers, edge servers, distributed geographically all around the world. Think Akamai, Cloudflare, CloudFront. While they're great for static files, many CDNs can also cache dynamically generated API responses for short periods. Their primary benefit, though, isn't just caching itself, but drastically reducing network latency. Remember, latency is often limited by the speed of light, how long it takes a signal to physically travel from the user to your server and back. By placing cache servers much closer to the end users, CDNs minimize that travel time. It's like having mini warehouses of your website's content or API results right in the user's city, so they don't have to wait for a package to travel halfway across the world from the main factory. That speed difference can be astonishing for user experience.
Okay, caching helps with repeated requests. But what if the data itself is just too large to fit or be managed effectively on a single database server, even a powerful one?
That's where partitioning, also commonly known as sharding, comes into play. The core idea is to split your data, which is too large for one node, into smaller chunks or partitions. Each partition then lives on a separate node, or set of nodes. This increases both the total storage capacity, you sum the capacity of all nodes, and the request handling capacity. Requests can potentially go to different nodes in parallel. Usually there's a gateway service or routing layer in front that knows which partition holds which data and directs incoming requests accordingly.
What are the common ways to decide how to split the data? How do you assign data to partitions?
There are two main classic approaches, range partitioning and hash partitioning. Range partitioning splits the data based on a key range. For example, if you partition by user ID, maybe users AM go to partition 1 and users NZ go to partition 2. It's simple to understand and efficient for range queries, like get all users starting with B. The big challenge with range partitioning is the potential for unbalanced partitions and hotspots. If, say, you partition by date, all your new data might land on the last partition, overloading it while older partitions sit idle. Dynamic partitioning, where partitions can automatically split or merge based on size or load, can help mitigate this, but adds complexity.
And the other approach, hash partitioning.
Hash partitioning uses a hash function on the partition key, like the user ID. The output of the hash function determines which partition the data belongs to. This usually leads to a much more even distribution of data across partitions, assuming a good hash function. The problem here, range queries become inefficient because related keys, like users A and B, are likely hashed to different unrelated partitions. You'd have to query all partitions. Also, while hashing distributes data well initially, adding new partitions can be painful if you're just using a simple modulo operation, like hash key %num partitions. If you increase num partitions from, say, 4 to 5, the result of the modulo changes for almost every single key. This means you'd have to reshuffle nearly all your data across the cluster, which is incredibly disruptive and resource-intensive.
Yikes. So how do you add capacity, add new partitions without that massive reshuffle?
This is where the elegance of consistent hashing comes in. It's a clever technique designed specifically to minimize data movement when partitions are added or removed. Imagine a conceptual ring or circle. Both the partitions, servers, and the data keys are mapped onto points on this ring using a hash function. A key is assigned to the first partition it encounters, moving clockwise around the ring. Now, when you add a new partition, it gets placed somewhere on the ring. Only the keys that fall between the new partition and the next partition clockwise need to be moved to the new partition. On average, if you have n partitions and k keys, adding a new partition only requires shuffling about kn+1 keys, a small fraction, instead of almost all of them. It's a fundamental technique used in many distributed hash tables and systems like Dynamo and Cassandra.
Okay, so we've partitioned our data, maybe partitioned our application servers too. Now we have multiple instances of things running. We need something to distribute the incoming requests among them. Enter the load balancer.
Exactly. A load balancer sits in front of a pool of back-end servers, like your web servers or application servers. Its primary job is to distribute incoming client requests across those servers. This effectively decouples clients from specific server instances. Clients just talk to the load balancer's address. It also enables fault detection. The load balancer can stop sending traffic to servers that appear unhealthy.
How does it decide which server to send a request to? Are there different strategies?
There are many. The simplest is probably round robin, just send requests to servers in a rotating sequence. Server 1, then 2, then 3, then 1 again.
Oh.
It's simple but doesn't account for server load or capability. More sophisticated algorithms exist. A surprisingly effective one, often called power of two choices, is to randomly pick two servers from the pool and send the request to the one that is currently less loaded of the two, based on recent metrics like active connections or response time. This simple randomized approach often achieves much better load distribution than pure round-robin, even if the load metrics are slightly delayed.
And you mentioned fault detection. How does the load balancer know if a server is unhealthy?
Through health checks, the load balancer periodically probes each server in its pool. This could be as simple as checking if the server responds to a TCP connection attempt or an HTTP request with a 200 OK status code. More advanced checks might monitor CPU usage, memory, or application-specific metrics. If a server fails multiple consecutive health checks, the load balancer marks it as unhealthy and temporarily removes it from the pool of active servers, stopping traffic flow to it until it recovers and starts passing checks again. A really smart load balancer might also have logic to detect widespread failures. If, say, more than 50% of the servers suddenly appear unhealthy, it might temporarily ignore the health check results and keep routing traffic, assuming the health check mechanism itself or a downstream dependency might be the problem, to prevent causing a complete outage.
Are there different types of load balancers operating at different network layers?
Yes, that's an important distinction. The simplest, arguably, is DNS load balancing. You just configure DNS to return multiple different IP addresses for the same host name. Clients will typically pick one randomly or round robin. The big downside is DNS caching. If one server IP goes bad, clients might keep trying to connect to it for the duration of the DNS TTL, making it not very resilient for rapid failure recovery. It's mostly used today for a global DNS load balancing, directing users to different data centers based on geography, for instance.
Okay, so DNS is limited. What's next?
Then you have transport layer, or layer 4, L4 load balancers. These operate at the TCP UDP level. They typically work by presenting a single virtual IP address, VIP, to the outside world. When packets arrive at the VIP, the L4 load balancer rewrites the destination IP address to one of the real backend server IPs and forwards the packet, often without even terminating the TCP connection itself. They are very fast because they don't need to understand the application protocol, like HTTP. They can be scaled using clever networking tricks like Anycast, where multiple load balancer instances announce the same VIP and routers send traffic to the topologically closest one, and ECMP, equal cost multipath routing, allowing traffic for the VIP to be spread across multiple network paths and load balancer instances. The limitation is they lack application-level intelligence. They can't make routing decisions based on HTTP headers or terminate TLS connections, for example.
So for that application intelligence, you need.
You need an application layer or layer 7, L7 load balancer. These are essentially HTTP reverse proxies. They terminate the client's TCP and TLS connection, fully understand the HTTP requests, and then make routing decisions based on things like the URL path, HTTP headers, or cookies. Because they handle full connections, they can do useful things like demultiplex multiple HTTP2 requests coming over a single TCP connection to different backend servers, terminate TLS decryption, offloading that from your app servers, perform rate limiting based on API keys and headers, or implement sticky sessions, sending all requests from a specific user to the same backend server using cookies. Sticky sessions can be helpful for applications with server-side state, but they also risk creating hotspots if some users generate much more traffic than others, overloading their assigned server. For load balancing internal traffic between microservices, a common pattern is using client-side load balancing, often implemented via a sidecar proxy deployed alongside each service instance, which is a core component of service mesh architectures like Istio or Linkerd.
Okay, this scaling journey leads us inevitably to evolving our data stores. We started with maybe a single relational database. Why do they often struggle to scale out?
Traditional relational database management systems, RDBMS, like PostgreSQL or MySQL, were largely designed in an era of single, powerful, scale-up machines. They excel at providing strong ACID guarantees and flexible querying using SQL, often involving joins across multiple normalized tables. Normalization, avoiding data duplication, was key when disk space was expensive. However, performing complex joins across potentially billions of rows distributed across many commodity servers, scaling out, becomes extremely challenging and often slow. Their locking mechanisms for ensuring ACID consistency can also become bottlenecks at high concurrency.
This limitation really paved the way for the NoSQL movement, didn't it?
Absolutely. NoSQL emerged as a collection of database technologies designed explicitly to overcome the horizontal scaling limitations of traditional RDBMS. Think systems like Cassandra, MongoDB, Couchbase, HBase. They generally prioritize high availability and massive scalability over the strong consistency and flexible join capabilities of relational databases. They often embrace relaxed consistency models, like eventual consistency or causal consistency, which are easier to manage across distributed nodes. They're also typically designed with partitioning, sharding, built in from the ground up. The trade-off is usually a lack of standardized query language, though some have SQL-like interfaces, limited or no support for joins across different data types, and often a need to store data in a denormalized way, duplicating information, to optimize for specific read patterns. Common models are key-value pairs, wide column stores, document databases, or graph databases.
You mentioned denormalization and optimizing for reads. It sounds like data modeling is quite different, maybe even more critical in the NoSQL world.
That's a crucial point. It's a common misconception that NoSQL means no schema or no modeling. In reality, effective use of NoSQL databases often requires more careful upfront attention to data modeling than relational databases. Because you typically can't rely on joins to combine data later, you need to design your data structures based directly on your application's primary access patterns and queries from the beginning. For example, Vitillo gives a compelling example of modeling customer orders. In a relational world, you might have customers and orders tables and join them. In a NoSQL wide column store like Cassandra, you might design an orders by customer table, where the customer ID is the partition key, determining which node the data lives on, and the order creation date is a clustering key or sort key, determining the order of rows within that partition. This structure allows you to efficiently query, get the latest 10 orders for customer X without any joins, because all of that customer's orders are co-located and sorted on disk. It's a fundamental shift. Model the data for the queries you will run.
So NoSQL prioritizes scale and availability, often relaxing consistency. Is there a middle ground, something that tries to bring back ACID guarantees while still scaling out?
Yes, that's essentially the promise of the NoSQL category of databases. Think systems like Google Spanner, CockroachDB, VaultDB, TB. This trend aims to combine the horizontal scalability and fault tolerance, often associated with NoSQL systems, with the strong ACID transactional guarantees and familiar SQL interfaces of traditional relational databases. They often employ sophisticated techniques involving consensus protocols like Raft or Paxos, distributed transaction protocols like optimized 2PC, and sometimes novel clock synchronization mechanisms like Spanner's TrueTime to achieve consistency across distributed nodes. They explicitly prioritize consistency while still aiming for high availability, recognizing, as CKP suggests, that perfect availability is impossible during partitions anyway. They try to offer the best of both worlds, though often with their own complexities and trade-offs.
We've covered a lot of ground on building and scaling these systems. Now let's turn to our fourth pillar, resiliency. How do we make sure these complex systems stay strong and keep working even when, inevitably, things break?
This is absolutely critical. Building resilient applications requires first embracing a fundamental truth. In any sufficiently complex distributed system, failure is not the exception, it is the norm. Components will fail, servers crash, networks lag or drop packets, disks die, deployments go wrong. You simply must design with failure in mind from the start if you want your application to stay online and serve users reliably. You have to understand what can go wrong.
So what are some of the most common culprits? What kinds of failures do we really need to watch out for and design against?
It's interesting, one of the leading root causes for major catastrophic outages isn't necessarily hardware failure, but actually configuration changes. Pushing out a bad configuration value, maybe a wrong database endpoint, an incorrect timeout setting, a faulty feature flag rule can have devastating effects. And these effects are often delayed, because the application might only read that faulty configuration value when it's needed later, making the root cause harder to track down immediately. Rigorous version control, testing, and gradual rollout of configuration changes are absolutely vital.
Okay, configuration changes. What else?
Obvious ones are single points of failure, or SPOFs. These are components where, if that single component fails, the whole system or a significant part of it stops working. Common SPOFs can include critical databases without replicas, specific network hardware, DNS servers, as we discussed, expiring TLS certificates, and even humans performing critical manual steps without backups or automation. Automation is key to mitigating many human-introduced SPOFs.
And network issues.
Network faults are pervasive. Beyond outright connection failures, slow network calls can be silent killers. A dependency that's not down, but just consistently slow, can tie up resources, like threads or connections, in the calling service, eventually causing it to slow down or fail, too. These are sometimes called gray failures, subtle, partial degradations that are hard to detect but can cascade through the system.
What about problems within a service itself?
Resource leaks are a classic internal problem. Leaking memory over time will eventually crash a process. Leaking other resources, like threads from a thread pool or sockets from a connection pool, by not closing them properly, can cause a process to slow down dramatically and become unable to handle new requests if external call timeouts aren't properly configured to release those resources eventually. Unexpected load pressure, maybe a sudden spike in traffic, or a denial of service attack can also overwhelm a system that isn't designed to handle it gracefully. And finally, there's the nightmare scenario of cascading failures. This is where a failure in one small component triggers failures in dependent components, which in turn trigger more failures, spreading virally through the system like dominoes falling. For example, one database replica fails, causing all its traffic to shift to its partner replica, which then gets overloaded and fails too, bringing down the entire database layer.
That sounds terrifying. So how do we start building defenses against all this? Redundancy seems like a first step.
Absolutely. Building in redundancy is foundational. We already talked about load balancers detecting and removing unhealthy server instances from rotation. But the system needs to be designed to actually function correctly, perhaps in a degraded mode, i.e. showing fewer features, when some of its instances are down. And you need automation to quickly spin up new instances to replace the failed ones. Geographic redundancy is critical for surviving larger-scale failures. Deploying your application across multiple availability zones, AZs, within a single geographic region is common practice. AZs are physically separate data centers with independent power, cooling, and networking. This allows you to tolerate the failure of an entire data center. Replication between AZs within a region often uses synchronous methods like Raft to maintain strong consistency because the latency is usually low enough, single-digit milliseconds. For even higher resilience against catastrophic regional events like hurricanes or earthquakes, you might use multi-region deployments. This involves replicating your application and data across geographically distant regions, for example, US East and US West. Due to the much higher network latency between regions, tens or hundreds of milliseconds, replication between regions typically has to be asynchronous, often leading to eventual consistency for globally replicated data.
Okay, redundancy helps survive failures. What about preventing failures in one part of the system from spreading and taking down everything? Isolating the blast radius.
Yes, fault isolation is about limiting the blast radius of failures. Certain types of failures can be correlated. For example, a specific malformed request, a poison pill, might crash any server that tries to process it. Or one particularly resource-heavy user or tenant, a noisy neighbor, might overwhelm the servers handling their requests. If all users share the same pool of servers, these correlated failures can take down the entire service. Partitioning the application stack somehow can help isolate these issues.
How can you partition effectively for fault isolation?
A really powerful, though complex technique described by Amazon is shuffle sharding. Instead of assigning users to distinct, fixed shards, partitions, you create many small server groups, shards. Each user is then assigned to a combination of several of these shards, forming a virtual shard unique to that user or a small group of users. The magic is that the failure of even multiple underlying shards is unlikely to take out any single user's complete virtual shard, because the user's assignments are shuffled. It reduces the probability of any given user being impacted by shard failures exponentially compared to simple partitioning. It dramatically reduces the blast radius for correlated failures affecting specific shards. A related broader concept is cellular architecture. Here, you partition your entire application stack, web servers, app servers, databases, everything into independent self-contained replicas called cells. Each cell might handle a subset of users or traffic. A failure within one cell ideally doesn't affect users in other cells. Azure Storage, for example, uses a cluster-based cellular architecture for account isolation.
Okay, those are architectural patterns. What about specific tactics or patterns a service can use when dealing with its dependencies, downstream services, that might be failing or slow?
Right, these are often called downstream resiliency patterns. The most fundamental one is simply using a timeout for every network call you make to a dependency. Never wait indefinitely. If the dependency doesn't respond within a reasonable time, give up and handle the error. This prevents your service's resources, like request threads, from being tied up forever waiting for a slow or dead dependency.
Giving up is one thing, but maybe the failure was temporary. What about retrying?
Retrying failed or timed out requests is another common pattern. But you have to be careful. If you just retry immediately and the dependency is overloaded, your retries might just make the overload worse a retry storm. The standard practice is to use exponential backoff with jitter. This means you wait longer before each subsequent retry, exponentially increasing the delay, and you add a small random amount of time, jitter, to the delay. The jitter prevents thousands of clients from retrying at the exact same moment after a brief network blip. But beware of retry amplification in systems with long chains of dependencies. A calls B calls C. If each layer retries multiple times, a single failure at the bottom can trigger a huge number of retries cascading back up the stack. And again, retries make the concept of request idempotency, which we discussed earlier, absolutely critical. Retrying a non-idempotent request can cause serious data corruption or duplicate actions.
Okay, timeouts and retries handle transient issues. But what if a dependency is just consistently failing or slow for a longer period? Retrying constantly seems bad.
Exactly. That's where the circuit breaker pattern comes in, and it's a really powerful concept for building resilient systems. Think of an electrical circuit breaker in your house. If an appliance keeps drawing too much current and tripping the breaker, you don't just keep flipping it back on immediately. The breaker stays open to prevent damage. A software circuit breaker works similarly. It monitors calls to a specific downstream dependency. If the number of failures or timeouts exceeds a certain threshold within a time window, the circuit breaker trips or opens. While the circuit is open, the service doesn't even attempt to send new requests to that failing dependency. Instead, it fails fast, immediately returning an error or perhaps some cache and fallback data to the caller. This protects the calling service from wasting resources on calls that are likely to fail, and it gives the downstream dependency time to recover without being hammered by constant requests.
So it just stays open forever. How does it know when the dependency is healthy again?
It doesn't stay open forever. After a configured cooldown period, the circuit breaker enters a half-open state. In this state, it allows a single test request, or small number, to go through to the dependency. If that test request succeeds, the breaker assumes the dependency has recovered and transitions back to the closed state, allowing traffic to flow normally again. If the test request fails, the breaker trips open again immediately, starting another cooldown period. This pattern allows systems to achieve graceful degradation. For instance, Vitillo mentions how Amazon's front page might still render even if the recommendation service it calls is down, because the circuit breaker for that dependency tripped, and the page just renders without the recommendations section, rather than showing a total error page. It isolates the failure and allows the rest of the system to continue functioning.
That's really elegant. So those patterns protect us from downstream failures. What about protecting our own service from being overwhelmed by upstream callers or sudden load spikes?
Good question. These are upstream resiliency patterns. One is load shedding. When a server detects it's becoming overloaded, example, high CPU, memory pressure, request queue backing up, it can proactively start rejecting new incoming requests, typically with an HTTP 503 service unavailable status code. This preserves resources to finish processing the requests it has already accepted, preventing a complete meltdown. Load shedding can be simple, reject all new requests, or sophisticated, prioritize high-priority requests and reject low-priority ones.
What else besides just rejecting requests?
Load leveling is another approach, especially useful for handling bursty traffic. Instead of processing requests synchronously as they arrive, you can place incoming requests onto a message channel, or a queue, like Kafka, RabbitMQ, or SQS. Worker processes then consume requests from the queue at a more sustainable rate. This decouples the producers, sending requests from the consumers, processing them, and smooths out temporary load spikes, preventing the processing backend from being overwhelmed. The queue acts as a buffer.
And enforcing limits on callers.
Yes, rate limiting is crucial, especially for public APIs or multi-tenant systems. You enforce quotas on how many requests a specific client, for example, identified by an API key or IP address, can make within a given time window. AG 10 requests per second. Implementing this efficiently at scale can be tricky. Naive methods like storing timestamps for every request in a list don't scale well. More efficient approaches often involve token bucket or sliding window algorithms, often implemented using fast in-memory stores like Redis. Distributed rate limiting, enforcing a global limit across multiple servers, adds another layer of complexity, often requiring coordination or probabilistic approaches.
And you mentioned one pattern earlier that sounded almost counterintuitive. Constant work. How does that make a system more resilient?
Yes, the constant work pattern is fascinating because it can make a system anti-fragile, meaning it might actually perform better or become more stable under stress, not just survive it.
The core idea is to design components such that the amount of work they perform is independent of the load or the rate of change in the system. They do the same amount of work regardless of whether things are quiet or frantic. Vitillo gives the example of a control plane system that manages configuration for many devices. Instead of processing individual change events, which could spike during high load, the control plane might periodically, say every minute, compute its entire desired state for all devices and dump that complete state snapshot to a highly scalable file store, like S3. The devices, or a data plane, then periodically fetch this complete state snapshot. Even if thousands of configuration changes happen at once, the control plane does the same amount of work recalculate and dump everything. It's decoupled from the input rate, protecting it from overload spikes. It seems inefficient at first glance, but it provides incredible stability under pressure.
That's a really different way of thinking. Okay, we've covered building for scale and designing for resilience. Our fifth and final pillar is maintainability and operations. It's not enough to build it. You have to keep it running, fix it, and evolve it over time.
Exactly. And it's a well-known, almost sobering fact in software engineering that the vast majority of the total cost of a software system over its lifetime isn't in the initial development, but in the ongoing maintenance, fixing bugs, adding new features, adapting to changing requirements, and simply operating the system day to day. Therefore, designing systems that are easy to understand, modify, extend, and operate safely is absolutely crucial for long-term success and cost-effectiveness. Good design here pays dividends for years.
Where does testing fit into making systems maintainable and operable?
Testing is fundamental for building confidence that your changes are correct and won't break things. The test pyramid is a classic concept here. It suggests you should have a large base of small, fast unit tests that verify individual components or functions in isolation. Then a smaller number of integration tests that verify the communication and interaction between components. For example, does my service talk to the database correctly? And finally, at the very top, an even smaller number of end-to-end tests that simulate real user journeys across multiple services.
Can you elaborate on those different test scopes and their trade-offs?
Sure. Unit tests are great because they're usually fast to write and run, they're deterministic, pass or fail consistently, and they pinpoint failures precisely to a small piece of code. The downside is they don't test how components work together. Integration tests start testing those interactions, maybe involving a real database or network calls to other local services. They give more confidence about component collaboration, but are slower and potentially less reliable. Example, depend on external system state. End-to-end tests provide the highest confidence about the overall user experience, validating entire user-facing scenarios across multiple deployed services. However, they are typically the slowest, most brittle, prone to failing due to unrelated issues, and hardest to debug when they fail. You want some, especially for critical user journeys, but relying too heavily on them makes your test suite slow and fragile.
To make tests faster and more reliable, especially integration and unit tests, people often use test doubles, right? Fakes, stubs, mocks.
Yes, test doubles are used to stand in for real dependencies. A fake might be a simpler in-memory implementation of a component, like an in-memory database instead of a real one. A stub provides canned answers to specific calls made during a test. A mock goes further, not just providing answers but also verifying how it was called. For example, was the save method called exactly once with specific arguments? These doubles help isolate the component under test, making tests faster and more deterministic. The trade-off, however, is that the test environment becomes less like the real production environment. Overuse of mocks, in particular, can lead to tests that are tightly coupled to implementation details, making refactoring harder.
Is there anything beyond traditional testing for ensuring correctness, especially for complex distributed algorithms?
There is, and it's a fascinating area. Formal verification. This is a more rigorous approach. Instead of just writing example-based tests, you write a formal specification of your system's desired behavior, often using a specialized mathematical language, like TLA+ or Alloy. Then you use automated tools, called model checkers, to exhaustively explore all possible states and execution paths of your system model, or sometimes even your actual code, to mathematically prove properties, like the system never deadlocks, or find subtle bugs and edge cases that traditional testing might miss. Vitillo mentions examples like using formal methods to verify the correctness of complex database migration strategies, like dual writing, before implementing them, giving extremely high confidence that data won't be lost or corrupted during the transition. It's a powerful technique for critical, hard-to-get-right system components.
Okay, so we have tests for confidence. How do we get changes out safely and efficiently into production? That's continuous delivery, right?
Yes, continuous delivery and deployment, often shortened to CD, is a set of practices and automations designed to make software releases low-risk, frequent, and efficient. The goal is to automate the entire release process, from the moment code is merged into the main branch all the way to being live in production. This dramatically increases safety compared to infrequent, large manual releases and allows for faster feedback loops.
What do these CD pipelines typically look like? What are the stages?
A typical CD pipeline might have several automated stages. One, review commit stage, triggered on a pull request or merge, runs fast checks like static analysis, linters, and crucial unit tests, provides quick feedback to the developer. Two, build stage. If the first stage passes, this stage compiles the code, runs broader tests, maybe some integration tests, and creates the deployable artifact, example, container image, a binary package. 3. Reproduction staging stage. The artifact is deployed to a production-like environment, staging or pre-prod. More comprehensive tests run here, including end-to-end tests, performance tests, security scans. This is the final gate before production. 4. Production stage. If all previous stages pass, the change is deployed to production. This is almost always done incrementally using strategies like canary testing, releasing to a small subset of users first, or blue-green deployments, closely monitoring health signals.
What are the key safeguards needed to make CD actually safe?
Several things are critical. Using infrastructure as code, IAC, tools like Terraform or CloudFormation to manage and version control your infrastructure changes alongside your application code is vital. Testing the infrastructure changes is just as important as testing application code. Having sufficient bake time between stages, especially between pre-production and production, allows time to observe the system under load and catch latent issues. Continuous monitoring of key health signals, SLOs, metrics, error rates, alerts, we'll get to those, during and after deployment is non-negotiable. The CD pipeline itself must constantly assess the health of the deployment. If key metrics degrade after a change is rolled out, the pipeline should automatically initiate a rollback to the previous stable version. And crucially, to make rollbacks safe and feasible, changes should almost always be designed to be backward compatible, especially changes to data schemas or API contracts. You need to be able to run the old and new versions side by side during the deployment, and roll back without data loss or incompatibility issues. This often requires careful planning, like multi-stage deployments for breaking changes.
You mentioned monitoring health signals. That brings us to monitoring. How do we know if the system is actually healthy once it's running?
Monitoring is about understanding the health and performance of your system in production. It goes beyond just knowing if a service is up or down. We can distinguish between black box monitoring, which checks the system from the outside like a user would, e.g. pinging a health check endpoint, running synthetic transactions, and white box monitoring, which looks at the internal state and behavior of the system. Example, CPU usage, memory queue lengths, application-specific counters. Etsy famously popularized white box monitoring at scale with their stats tool.
What are the core components of a good monitoring system? What kind of data do we collect?
Metrics are a cornerstone. These are time series data numerical values measured periodically over time, like CPU utilization, request latency, error counts, queue depth. Metrics are often associated with tags or labels, like region, host, service name, API endpoint, that allow you to slice, dice, and aggregate the data for analysis. Example, show me the average latency for the login endpoint in the EU region. Collecting metrics with too many unique tag combinations, high dimensionality or high cardinality, can become costly for storage and querying, so techniques like pre-aggregation at the collection agent, calculating sums, averages, percentiles over short intervals, are often used to improve efficiency in systems like AWS CloudWatch or Prometheus.
How do we choose which metrics are most important for understanding service health from a user perspective?
That's where service level indicators, or SLIs, come in. SLIs are specific, measurable metrics carefully chosen to indicate the level of service being provided, usually reflecting things users directly care about. Common SLIs include request latency, how long things take, error rate, how often things fail, throughput, how much work is being done, and availability, a percentage of time the service is usable. SLIs are often defined as a ratio of two metrics, for example, number of successful requests, total number of requests, 100 for availability, or number of requests served faster than XM's total requests, 100 for latency compliance. This ratio format makes them easy to interpret as percentages between 0 and 100.
You mentioned latency. I often hear people talk about averages, but Vitillo emphasizes long-tail latencies. What are those and why are they so critical?
This is a hugely important point. Long-tail latencies refer to the experience of the slowest requests, often measured using percentiles like the 95th, P95, 99th, P99, or even 99.9th, P9.9 percentile. P99 latency, for example, tells you the maximum time that 99% of your requests completed within. That remaining 1% took even longer. Why is this crucial? Because averages hide outliers. Your average response time might look great, say 100 meters, but your P99 might be 2 seconds. That means 1 out of every 100 requests is taking 2 seconds or longer, which is likely a terrible user experience for those affected. High long-tail latencies not only hurt user satisfaction, and studies show they directly impact revenue, but they can also destabilize the system itself. Slow requests hold on to resources like server threads or connections for longer, which can lead to resource exhaustion and cascading failures under load. Monitoring and optimizing for percentiles, not just averages, is critical for robust systems.
Okay, so SLIs measure user-relevant health. How do we set targets for them?
That's the role of service level objectives, or SLOs. An SLO is a target value or range for an SLI, agreed upon by stakeholders, defining the acceptable level of service reliability. For example, an SLO might be 99.9% of login requests should succeed, or P99 latency for the search API should be below 500 meters. SLOs serve several purposes. They set clear expectations for users and internal teams. They also define an error budget, the amount of acceptable unreliability or failure allowed within a given period. Example, if your availability SLO is 99.9%, your error budget is 0.1% downtime. This error budget is a powerful concept. If the service is meeting its SLOs, the budget isn't being spent. Teams might have more freedom to release new features faster or perform potentially risky maintenance. If the service is violating its SLOs, burning through the error budget too quickly, it's a strong signal to prioritize reliability work, fixing bugs, improving performance, over shipping new features. SLOs help make data-driven decisions about engineering priorities and measure the real impact of incidents.
How do SLOs translate into practical alerts for the operations team?
Alerting is typically triggered when a metric, often an SLI, crosses a predefined threshold for a certain duration. However, simply alerting on raw SLO thresholds, like alert if availability drops below 99.9%, can be noisy and prone to false alarms during brief dips. A more effective approach, advocated by Google's SRE practices, is to alert based on the burn rate of the error budget. The burn rate indicates how quickly the error budget is being consumed relative to the SLO period. For example, a burn rate of 1 means you're consuming the budget exactly as expected over the SLO window, for 30 days. A burn rate of 2 means you're consuming it twice as fast and will exhaust the budget in half the time, 15 days. A burn rate of 10 means you'll burn through it in just 3 days. You can set up alerts based on high burn rates over different time windows. Example, alert immediately if the burn rate over the last hour is very high, indicating a sudden major outage. Alert with lower severity if the burn rate over the last 6 hours suggests you'll breach the SLO within a few days. This focuses alerts on situations that genuinely threaten the SLO.
Beyond alerts, how do teams visualize all this monitoring data?
Dashboards are essential for providing real-time visibility into system health. Good dashboards aggregate key metrics and SLIs, often tailored to different audiences. You might have a high-level dashboard showing overall SLO compliance for executives, another focused on public API performance for external partners, and more detailed service-specific dashboards for the engineering teams operating those services. Best practices for dashboards include clear chart layouts, consistent use of time ranges and units, meaningful annotations like showing alert thresholds or deployment markers, and avoiding overly cluttered displays. The goal is to quickly understand the current state and identify potential problems. And underpinning all this is a healthy on-call culture. Vitillo emphasizes that having developers operate the software they build leads to more reliable systems because they directly feel the pain of operational issues. Learning from production incidents through blameless postmortems is crucial for continuous improvement, ensuring that mistakes become valuable lessons learned.
Okay, monitoring tells us if something is wrong. But why is it wrong? How do we debug complex issues in production? That seems to require deeper insights.
Exactly. That's where the concept of observability comes in. Observability is often described as a superset of monitoring. While monitoring tells you whether the system is working, observability provides the tools and data to ask arbitrary questions about why it's behaving the way it is, especially for uncovering emergent behaviors and debugging novel or complex production issues quickly without needing to ship new code just to understand them. The three pillars of observability are often cited as metrics, logs, and traces. We've covered metrics. Let's look at logs and traces.
Okay, logs. We're probably all familiar with log files. How do they fit into observability?
Logs are immutable, time-stamped records of discrete events that occurred within the system. They can be free-form text messages or increasingly structured data, like JSON, which is much easier for machines to parse and query. Logs are invaluable for deep diving into the root cause of specific errors or unexpected behavior. When a metric tells you the error rate spiked, logs can often tell you what specific requests failed and provide detailed context, like stack traces or relevant variable values at the time of the event. They are crucial for investigating those long-tail issues or rare edge cases. Best practices for logging include trying to collate all relevant information for a single unit of work, like processing one request, into a single structured log event if possible, sanitizing sensitive information like passwords or PII, being mindful of logging volume and cost, as storing and processing massive amounts of logs can be expensive, and ensuring logs can be easily searched and correlated across different services.
And the third pillar, traces. What do they give us that logs and metrics don't?
Distributed tracing provides a way to capture the entire end-to-end journey of a single request as it propagates across multiple services in a distributed system. When a request enters the system, it's assigned a unique trace ID. As the request flows from one service to another, e.g. via HTTP calls or message queues, this trace ID is propagated along with it. Each service involved records information about the work it did for that request as one or more spans. A span typically includes the operation name, start time, duration, and potentially logs or tags associated with that specific operation. All the spans sharing the same trace ID can then be collected and assembled to visualize the entire request lifecycle, showing which services were called, how long each step took, and where potential bottlenecks or errors occurred. Tracing is incredibly powerful for understanding end-to-end latency, identifying hidden dependencies, and attributing resource usage across a complex microservices architecture. It helps you answer where did the time go for a slow request.
So metrics, logs, and traces really complement each other.
Absolutely. They provide different views into the system's behavior. Metrics give you the high-level overview of health and trends. Logs provide the fine-grained, detailed context for specific events. Traces give you the request-centric view of flow and latency across service boundaries. A mature observability strategy leverages all three, allowing you to detect problems with metrics, understand the end-to-end impact with traces, and dive into the root cause with logs.
Finally, under maintainability, let's touch on manageability. How can we make systems easier to configure and control dynamically?
Good point. Dynamic configuration is key here. Instead of hard-coding configuration values like timeouts, feature flags, connection strings into the application code or deployment artifacts, you store them in dedicated configuration management systems, like AWS App Config, Console, etc., or even just a database table. Applications are then designed to read their configuration from this external store at startup, and ideally to reread it periodically or react to push notifications at runtime. This allows operators to change system behavior, enable disable features, tune parameters, redirect traffic dynamically without needing a full redeployment of the application code, which is much faster and often safer.
And this enables things like feature toggles and A/B testing.
Precisely. Feature toggles, or feature flags, are essentially configuration settings that control whether a specific feature is enabled or disabled. Using dynamic configuration, you can release new application code with a new feature turned off by default. Then, once the code is deployed, operators can use the configuration system to gradually enable the feature, perhaps only for internal users first, then for a small percentage of external users, canary release of the feature, and eventually for everyone. This decouples feature release from code deployment, significantly reducing risk. You can also use feature flags for A/B testing, enabling different variations of a feature for different segments of users and measuring the impact on key business metrics to make data-driven decisions about which variation performs better. It gives you immense flexibility and control over how your system behaves in production.
Wow. So, we've really journeyed through the incredibly intricate world of distributed systems today. We've explored how these complex applications communicate reliably over unreliable networks, how they coordinate their actions using consensus or avoiding it, how they are built to handle massive scale, how they stay remarkably resilient even when failures are constant, and how they are kept running effectively through careful maintainability and operations practices. Hopefully, you now have a much more solid grasp of the fundamental challenges and the truly ingenious solutions that power almost every single digital interaction you have daily.
It really is amazing when you stop and think about it. Consider a seemingly simple online service you use every single day. Maybe sending a message to a friend on a chat app, streaming a short video clip on your phone, or ordering groceries online.
After this deep dive, what is one aspect of that system that you now realize is actually an incredible feat of distributed systems engineering? And perhaps how might that system silently fail in ways you never considered before, impacting your experience subtly, maybe without you even knowing precisely what went wrong? Something to ponder.
Absolutely. And if you're eager for more of those aha moments and want to go even deeper toward an expert-level understanding, Roberto Vitillo's book, Understanding Distributed Systems, is packed with references to the groundbreaking original industry papers that shaped this field papers describing systems like Windows Azure Storage, Dynamo, or Azure Data Explorer. We really encourage you to follow your curiosity down those rabbit holes, explore those original sources. That's where you'll find the really deep insights for the people who built these systems. It's a fascinating field to keep exploring.